Okay, it's now my pleasure to introduce Tim Lenton, whose name you've heard a number of times today already from Martin and others, and we're going upward in scale from mere economics and finance and mere ecology now to the scale of the entire planet. Tim?
Thanks, Chris. Thank you, Katja, as well. You've just given me more time to try and explain climate dynamics. I hope there's something in this that's of interest to those of you thinking about the stability of markets. I will briefly touch on some overlaps to economics at the end, but I'm going to start by talking about what do we think is the potential for abrupt change or tipping points or critical transitions in the Earth's climate system. How do we identify those? And then can we get early warning signals of them when we know they've happened in the past? Were there warning signals beforehand? If we run our models and force there to be threshold changes in the climate, can we see the warning signals before they happen? Completely agree with Doyne that you want to do a good job as a scientist. You want to get into the gory details of the climate system, and I do that as well, and so do my colleagues. But this talk is sort of about what we might learn from the very generic methods and ideas that Martin Scheffer explained nicely this morning, if we apply those into this very complex climate system. So, the guiding questions for my talk, what and where are these climate tipping points? Do they carry early warning signals? And when they don't, why is the method failing, and is it consistent with the theory? And then hopefully some time to reflect on what can or should or will we do about them. So let me start with what, to use probably a lot of wiggly coloured lines, but what I'm going to try and explain here is something about past abrupt climate changes. So we're looking at the last 100,000 years, basically the last ice age cycle into the present interglacial warm interval, the last 10,000 years here. The blue wiggly curve is come from an ice core drilled in Greenland, and it's essentially a measure of temperature, warmer upwards and colder downwards. So there's the last glacial maximum, the depths of the last ice age. If you're curious, these other green and red lines, they're high-resolution marine sediment records, but they tell us something about monsoon systems in northern South America, in Amazonia in red, and in Indian subcontinent in green. Let's look at the blue line. So we come into the last ice age. What you note are lots of abrupt shifts upwards, warming events. These are known after the people who first described them as Danskard-Oshka events, and each of those jumps upward are 8 or 10 degrees of warming in Greenland. And when we can resolve the timescale of the jumps well, in some cases there's 8 or 10 degrees of warming in about 5 years. So that's a truly abrupt climate change. And in our part of the North Atlantic region, well, it might not have been quite that much temperature change, but by God that would have been a shock. You see that and there are 20 odd of these in the last ice age, so that's a pretty volatile climate system. We think these jumps are linked to fundamental reorganizations of the Atlantic's overturning circulation, coupled to the atmospheric dynamics, coupled to the sea ice in the North Atlantic. But all of that also turns out in some way to be coupled to the monsoon system, so what we would call the intertropical convergence zone, the band of maximum rainfall that seasonally fluctuates in the tropics, and whether it switches on or off the monsoons in the northern hemisphere or just into the southern hemisphere. And basically what's happening is when there are abrupt climate changes up in the high northern latitudes, there are also abrupt shifts in the monsoons, and when they switch on in India, they're switching off in the Amazon and vice versa, because of the way this band of rainfall is shifting compared to the equator. So this is a coupled climate system, and these are not just localized events. Their repercussions are felt certainly throughout the northern hemisphere and the tropics, and some work on how they extend into the southern hemisphere. Now, we usually, as climate scientists, take some comfort from the fact that there's not as much going on in the last 10,000 years. The Holocene, as it's called, in which all our agricultural systems are developed and our civilizations developed, is more stable than the Ice Age, that's for sure. But it's not completely stable. So if this is a cave stalagmite record from part of China, Dongyi Cave, and it's all just wiggly lines to you again, but basically upwards is stronger monsoon, downwards a weaker monsoon. There's a lot of jumping around going on. This is the last 8,000 years coming towards the present. But in here are buried some quite abrupt shifts in that part of the Southeast Asian monsoon. Abrupt shifts that are definitely correlated with historically recorded cultural events in the region, like I've put one of them on the map, the collapse of Neolithic culture in China. So we know there's been abrupt shifts in the climate in the last 10,000 years, and we can correlate several of those to profound changes in human societies. So, well, what's our model then for these in this case, natural, quote-unquote, climate changes? Because we don't think that the human influence on the climate system at the time was global in scale like it is now. So how are we going to explain those? Well, one model would be the model that Martin walked us through earlier, the model of a bifurcation type tipping point where we're perhaps in a situation where there are two stable states of the climate, two valleys if you like, and a hilltop in between them. But the state we're in is losing stability, losing resilience as Martin described it. The valley is getting shallower to the point where it goes flat. The system bifurcates in a mathematical language, and the ball has to leave that valley which has disappeared and roll off into the other state. So that's the system, that's the model, if you like, where we could in principle get early warning signals if we move slow enough on the x-axis compared to the internal timescale of the system here. And as we'll see, there are some cases where we think that is what's going on in the climate system. You know, as major changes are happening, the Earth's orbit's changing, ice sheets are growing and shrinking on the northern hemisphere, we are seeing fundamental changes in the shape of the valleys and the hilltops, if you like. But there's another possibility, which is even if you don't move on the x-axis, your boundary conditions, the Earth's orbit, whatever in this case, might be fixed. But if you're in a fairly shallow valley here, and not too far from a hilltop, and there's quite a lot of variability in the climate system, as we know there was in the Ice Age, there's a chance your ball's going to get nudged several times in the same direction over the hilltop, and it'll roll off into the other valley. So I just cartooned this on here, but there's textbooks on this. It's called noise-induced transitions. And in a way, that noise-induced transitions could perhaps best be our null model for some of these abrupt past climate changes. And our job should really be to ask statistically whether we can falsify that null model in favour of something like this. And the bottom line actually with a lot of those abrupt climate changes in the Ice Age is it's very hard to falsify this as the null model, that there are just noise-induced switches in the climate system. Now that's kind of profound, because if there's no movement on the x-axis here, there's no early warning signal in a dynamical system sense. However, as we'll see, this is an area of active research, and there's a mixture of both processes going on always, and we do have reason to believe that there really are movements on the x-axis, and there are sometimes early warning signals, as I'll show in a bit. In the case of human activities, we're certainly a force on the x-axis now. We're definitely forcing the climate, but we'll come back to how quickly we're doing that and whether that violates the theory here of early warning, because we need it to be slow for the theory to work. So anyway, colleagues and I drew up a kind of map where we tried to identify, on the basis of what we know about past abrupt shifts in the climate system, on the basis of our models of the system and what they do under future forcing, and also just based on our fundamental understanding, we tried to draw up a map of potential, what I call tipping elements in the climate systems, bits of the planetary machinery, components, if you like, of the network of the climate, which could potentially exhibit abrupt shifts under the kind of forcings that we're putting into the climate system, which are, we principally think of building up greenhouse gas concentrations, but we're also emitting an awful lot of aerosols, especially in these Southeast and Southern Asian regions of the world, and that has a potential to interfere with the monsoon systems. Well, I'm not going to be able to go through all of the cases here, but in blue we have systems which are really about ice melting at some level, and there being alternative states, like if we could remove the ice sheet from Greenland under the present climate, it wouldn't be able to regrow, because down at sea level it's a lot warmer and you can't, the last winter's snow can't survive the summer, so that's a multiple stable state system. We have in red changes in the circulation of the ocean and atmosphere, or the two of them coupled together, or to the land surface. So that will be things like the potential to seriously disrupt the West African monsoon, to stop it making its seasonal jump northwards into the Sahel and just have the rainfall locked to the coast of West Africa. We see that in some future model projections. And in green, we've got the possibility that some major biomes or major ecosystems that are quite closely coupled to the climate might show alternative states and be tipped into them. And I'll come back to the example of the Amazon rainforest, where a lot of the rainfall in the Amazon has been recycled through the forest at least once, if not several times, by the time you get to this side of the basin. And if you took the forest away, it dries the system out, it can't recover. So there's a potential, and we see it in some of our projections, for Amazon dieback if there's a drying of the climate in that region. So that's just a loose idea simple idea there, that there's more than one of these potential tipping points. But remember, the climate's a connected system, so they're not totally independent. This is just a flavour, an out-of-date flavour as of what our understanding was 7-8 years ago about where we thought thresholds might be. And we like to express our uncertainty here with these burning embers colour scales, where for me, going from white into yellow means going towards from no probability to some probability, and going yellow to red is passing through as likely as not. Actually, nowadays, we would say, subsequent work, we would bring down the proximity of the thresholds in the Arctic, so the potential to lose the Arctic summer sea ice or the Greenland ice sheet, probably at lower global warming above the 2000 level than we suggested here. I think the take-home messages are there are quite a few of these potential tipping points. Of course, we don't know exactly where they are. This is the kind of information we get from our models, our current understanding. But we'd like to think about whether we can get better early warning. One other piece of information about the likelihood of these different tipping points. This is a very complicated slide, but it's basically the results of an expert elicitation. And what's going on here is, well, yeah, we're climate scientists, we build climate models, but as the people who build and use the models, we know the weaknesses in them. So we have some faith in our models, and we're also pretty aware of where they're flawed. And we use a process like an expert elicitation. It's where you have a sort of a formal questionnaire almost, and an iterative process with the experts, where you try to expose from their knowledge, from their models, but also their knowledge of the weaknesses of the models, what are they going to say about the likelihood of tipping a particular system under a particular warming corridor. So this is less than 2 degrees of global warming, 2 to 4 degrees, or more than 4 degrees on the time horizon of the next couple of centuries. And all of these bars range in the scale between 0 and 1, and they're the imprecise probability ranges, each bar from a particular expert, and the coloured bits are aggregations of those probabilities. We don't need all the details to see that in all cases these are quite significant probabilities. Even under low warming, we're not talking about everyone sitting on the 0 probability line. We're getting answers of a quarter on average for tipping major bits of the climate system. So even in the conservative assumptions, if you aggregate those assessments together, you come back with the sort of aggregate probabilities at the absolute lower bound on tipping 1 out of 5 bits of the climate in middle sort of warming range is minimum 16%, and in business as usual, which is 4 degrees of warming in the next century or so, the lower bound is at 56%, so it's already above more likely than not. And the take-home message from that is we're not talking about a high-impact, low-probability event. That's a high-impact, high-probability event, right? And that's interesting because the economics of climate change, until very recently, was basically operating on the assumption that these are high-impact but very low-probability events. And in economic models, very low probability was meaning, well, 0.01 perhaps, but certainly nothing like this level. All right. The other thing, by the way, that comes out of this kind of pooling of knowledge, expert elicitation, was some structure about how different tipping elements or parts of the climate system might interact. If you tipped one, would it increase the likelihood of tipping another or decrease it? So this is the very beginnings of a crude network view of our planet. where you can kind of ask the question, have we got domino dynamics? If I tip one domino, is it going to tip the next, and so on and so on? Gosh, that would be very bad news, and it would amount to everything coming up red or a plus sign on this diagram. If you look carefully, there is slightly more red than green on here, slightly more pluses than minus. But of course, it almost can't be the case that it's all red and it's all domino-like, because we've had 3.5 billion years of life on the planet with a relatively stable climate. It can't be a fundamentally unstable system, the Earth. Actually, we have reason to believe, because of the recent ice age dynamics and the stuff that I've shown you, that actually, regardless of humans, the Earth is in a rare state where it's peculiarly unstable compared to its normal, pretty resolute, resilient, stable configuration. So that's sort of reflected here in this red coloration, and the idea that there is some interaction where if we tipped a bit of the system, it might tip another bit, and so on. Okay, so that's a bit of backdrop, and then on to the early warnings story. So Martin walked us through the theory here, and I think what Katja is doing is, at the methodological level, going to be very similar, actually, as to how we try to measure this cartoon here of loss of resilience of a system. So we're imagining we start, a system has two alternative stable states. You can only be in one of them, and that's the solid ball. And we're going to force it slowly to the point where this state that it's in loses its stability, and the ball is going to have to roll off into the other state. That's the bifurcation point. We can imagine that this ball is not static. In the climate, there's a short-term stochastic process that we call the weather that's moving the ball around all the time, and we can watch how quickly the system falls back to its lowest energy state, the bottom of the valley. And it'll fall back quickly here in this nice stable configuration, and it'll recover more slowly here and even more slowly here, and so on. And the curvature of the potential well, as a physicist calls it, is actually directly formally related to the timescale tau here of the recovery or decay from fluctuations. I haven't put the maths in the talk though. Perhaps that's a good thing. But I like the video. I prefer the video version of this. So here's an example where we're destabilizing this state, and this state's going to get more and more stable, and eventually the system's going to tip, but it's subject to some white noise, some stochastic forcing. And hopefully you can see by eye over time that the ball here is recovering more slowly, or the system's recovering more slowly from fluctuations. The x-axis here is just becoming the y-axis over here, and we have time. So this is this critical slowing down phenomena that Martin introduced, just a real mathematical example of that. And it's about to tip to, oh, it's gone, just before the bifurcation point. And the question is, well, what can we do in terms of time series analysis as this is running along to extract the signal of slowing down of the fluctuations? And there's several measures you could use, but even a really crude measure, which is lag 1 autocorrelation, how similar to the last point is the present point, estimated over some window of points that's sliding along the time series. That turns out to be a pretty good way of extracting the fact that there's slowing down going on, or in other words, there's increasing memory in the system, which I think is very much like what Katja was getting at in her analysis. So this is the same example. We're going to cut the time series before the transition. We're going to get rid of any drift, so any red line drift in the series, because we don't want non-stationarity. We're just going to analyse the residuals here, the fluctuations around the long-term mean of the series. And now you'll see an estimate of lag 1 autocorrelation, the AR1 coefficient, plotted in red on this sliding window of probably, let's say, 500 points or something there. And it should go up as a reflection of slowing down and the fact that these fluctuations are longer lived, and that sure enough it does. I mean, not universally upwards, but we can put a statistical measure on that. We can use a thing called a tau rank correlation coefficient, or something cruder, just to state how strongly there's a rising trend in that indicator. And then we can construct a null model and test the significance of that rise in indicator against the null model. And that's the kind of game we play now when we go to real test cases. So what I want to do now, having kind of given you the the video is go to some real examples and see if the method works in anger on the real climate system. Time is good. All right, so let's try the exit from the last ice age. A bit of a turbulent affair. So this is 22,000 years ago. This is about 12,000 years ago. I've cut out the exit into the Holocene, the nice, relatively stable bit of the climate civilizations have been developing in. This is again a Greenland ice core record where basically temperature is upwards. There is some big warming event here that we know about. It's called the boiling Alarod, before another cooling in the North Atlantic region called the Younger Dryas. And you can see that our detrending isn't perfect, so we're having some issues taking out what's already an abrupt climate shift there. If we look at the residuals, though, actually even before we get to that point, we could arguably see by eye that there's starting to be some slowing down, and that's being measured with this AR1 coefficient down here. Then this inability to get rid of that is kind of artificially producing a jump in our indicator. But then even by eye, you can see there's really long-lived slow fluctuations in the climate system as it's starting to, before it finally jumps out of the ice age. There's a bit of nuance to it if we want to ask questions later, because it cools down again and then it almost gets more stable. But there are some very long-lived fluctuations that you never saw in the depths of the last ice age 20-odd thousand years ago, before you finally flip out in what was a kind of 8-10 degree warming in Greenland in something like 5 years here that I mentioned earlier. So that does look like it's a case where there's a slow, really slow forcing in the system. You could think of that as the Earth's orbit is changing very slowly, and also an ice sheet in the or ice sheets in the northern hemisphere are relatively slowly melting. And then other parts of the climate system with faster dynamics, the ocean, atmosphere, sea ice system jumps on a faster timescale, but you're able to sample the system even faster than that. So you have the right separation of timescales that you can pick up the early warning. So I mentioned a bit about the overturning circulation of the ocean. Have you heard of this thing, the thermohaline circulation? It gets some press these days. It's been in the newspapers. So this is the heat and salts, if you like, transport the major flow of the world ocean. And in the Atlantic, you have a surface current that's heading from the Southern Ocean northwards across the equator, all the way up to the North Atlantic, and deep waters forming to the west and to the east of Greenland, and the blue is the return circulation at depth. So this makes our bit of the world where we are today a lot warmer and milder, especially in the winter, than say the equivalent latitudes over here. And there's plenty of theory to support the idea that although we have this overturning circulation of the Atlantic now, there's an alternative stable state where it's switched off, and it stays switched off. This black line is an effort that already exists to monitor this overturning circulation with an array of scientific instruments across 24 degrees north in the Atlantic, and that's just a little cross-section of what's going on there. You're at the start of the Gulf Stream near Florida that's going to flow northwards, and you have a return flow at depth. So there's the beginnings of the idea that we're trying to monitor this, perhaps to get some early warning of whether there could be a future collapse of the overturning, because we don't want it to collapse. It would cool down the winters radically if we lost this flow of heat in the Gulf Stream here. What I want to do now is just show some cases where in a climate model world we can force this thing to collapse, and then we can ask ourselves, well, in the model experiment at least, can we see any early warning signals before this fundamental reorganisation of the ocean circulation? So I got, just for confusion, I got two different models that are different levels of complexity basically. Both of them I'm forcing what's on the y-axis is this overturning circulation of the Atlantic, a measure of that in Sverdrup's million cubic meters per second of water flow, and I'm slowly forcing it to collapse. In this case, it's a simpler model with a three-dimensional ocean but a less sophisticated atmosphere model, where I'm having to impose some sort of white noise to mimic the real weather. Here I've got a more fancy model, though I can't afford to integrate for as long, so the x-axis of time is 5,000 years rather than 40,000 years. But I've got, it's like a weather forecast model. It has an atmosphere model on top of an ocean model, and the atmosphere has its own chaotic dynamics that's generating the internal variability in the ocean circulation strength, the sort of wiggling of the black lines here. And again, well, not only is it eventually going to collapse, the Atlantic overturning, but there's some sort of shutdown here where it shuts off the deep water formation in the Labrador Sea before it shuts off on the other side of Greenland. So we could look at those time series, take out the trends, look for the early warning indicators. What do you get? With the auto-regression at lag 1, you get the black lines here. That looks pretty good. This brown area over here is sort of some checks on that measure by changing the detrending we use on the data, changing the length of the sliding window, checking for robustness. We always get a really robustly rising indicator in that model, so a really good early warning signal. But here, notice we force the system really slowly, so we meet the conditions of the theory here, that the theory ought to work, it does work, that's good. In this case, there's also a pretty good warning signal, especially before this partial shutdown of the circulation, and arguably not so good after that, before the final collapse. And when you check, is this method robust, it doesn't look so good, is what those colours are showing over there. But we dig a bit deeper, we find that if we don't filter the data the right way, then we lose the warning signal. But we can physically understand that as climatologists, because if we, for example, filter the data wrong and we eliminate all the long time scales in the system, we're left looking just at basically how the atmosphere's fast dynamics are just being manifested in the ocean. The wind's changing direction and the circulation's following the wind. And what we need to be extracting here is the longest time scale of the ocean that's itself slowing down. So basically, in a nutshell, if we understand the system, we think about that properly, we wouldn't be doing a sort of treatment of the data down here, and we would recover the signal. If you're curious what the dashed lines are, they're another way of looking for this slowing down, but by using slightly fancier time series analysis that's called detrended fluctuation analysis. Maybe you know it with your work with financial time series, maybe you don't. You can ask me questions about it later if you're curious, but that's just one of many, I would say, slightly fancier methods of looking at how correlations decay in time series. So some maybe encouraging results there, but here I want to head in the direction of thinking, well, is this really going to be useful in anger when humans are forcing the climate system and we're forcing it quite quickly? So this is from another piece of work we've been doing with an even more complicated model, which also has, happily, early warning signals of this collapse of the Atlantic's overturning circulation. But you can ask the question, how long, in a statistical sense, before I get a robust warning signal relative to some null model, which in this case would be like what we call a control run of the climate model without any forcing. And the answer comes back, well, you've got to monitor the ocean for something like 550 years, and then in the high northern latitudes and then in the high southern latitudes of the Atlantic, you can get a robust warning signal that stays with you, and that robust warning kicks in about 200 years before the collapse of the Atlantic. So you've got good news on the one hand, that's a very early warning, 200 years before the collapse. Bad news on the other hand, you need to have been monitoring the system for several hundred years. And we haven't been observing the ocean for several hundred years directly. We've had thermometers on ships for a couple of hundred years, and we have other ways of reconstructing the past ocean circulation strength. So this is not a hopeless case, but it's quite hard science to get this measure of what the ocean was doing before. And the other thing to remember is this is a bit of an artificial experiment where we force the model relatively slowly, and you could argue that humans are forcing the climate quite quickly, which could violate the possibility for early warning. So let's have a little look at that with a different case study. So I'm just going to jump to another of my candidate tipping points, which is that we might trigger dieback of the Amazon rainforest if we don't just chop it down anyway, which has been underway for a while. So what's up here? Well, first thing to know is there are very interesting things going on in the climate in Amazonia anyway. So 2005 and 2010 were both, there were national emergencies declared in Brazil because of the droughts in the Amazon. A rainforest forest had drought in both of those years, and that's what this coloured plot is about. Large areas of exceptional drying in the Amazon basin. And this is the reason I put that up is because that's the concern for the future. There is an observed trend of drying in this region. If we were to extrapolate it forwards, eventually we get to a point where the trees will be in trouble. They'll get the rain they want in the wet season, and they don't mind the beginning of the dry season because they've still got water in the soil they can tap into. But if the dry season's too long, they run out of water, that's it. Fires sweep through the forest, the trees die, they cavitate, and that happens in some of the climate models. It happens in the UK Hadley Centre model, or some versions of it. So for what it's worth, that model can show dieback like kind of in this Lego brick world of a climate model over big chunks of the Amazon. Experts say there's a decent likelihood of this being a possibility. The one other thing to say is that the Amazon system, the forest, yeah, it's coupled to the climate, but humans change the climate so fast in the model simulations going along the black line here that the forest the equilibrium state of the forest can't keep up with the climate. It's lagging behind the climate. So if you were to freeze the climate at 2 degrees and just keep it going at that level and let the forest respond, you'd actually find quite a large forest loss already. 3 degrees, even larger loss, and that's what the dotted line plots here. It's like the committed dieback of the forest that you haven't realised yet. And the important idea there is this idea of lag. The forest is showing no signs of dieback at all at 2 degrees or 3 degrees of warming, which in this model, this is like the 2030s, 2040s, a few decades' time, but it's already committed to a much larger loss. So what we did is we took about 50, 60 versions of this model with different physical parameterizations, where there was dieback in lots of examples of the model, and we asked, are there early warning signals before the forest dies back? And the bottom line was not really reliable ones. And that was interesting because we could look at the mathematical equations of the model that told us that there was a bifurcation in the equations, that the theory would tell us there should be a warning signal there. So we must be violating some other parts of the early warning theory. And what's happening here is we are indeed basically breaking the mathematical theory, where the human activities as simulated are too fast. They're on a comparable timescale to this sort of 50-year dynamical timescale of the forest, of regrowing trees or whatever. And that means that theoretically, we can run the model and show the theory should break. We should lose the warning signals. Indeed, we did. We picked up some increased variance, some increased variability as a common in these model simulations, which is also something you'd expect to happen if you were losing resilience, as Martin described it, and you were living in an ever shallower valley. Every nudge you got would move you further, so the variance of your data, your experience would increase. We picked that up, and you might try and persuade yourself that was a warning signal. But if you look in the climate model, you find that the variance in the climate itself, say the temperature and the precipitation that forced the trees, that was going up. So all the forest was doing was just kind of mimicking the forcing. So the rapid forcing here, relative to the timescale of this bit of the climate system, was basically destroying the potential for warming, early warning. But that doesn't mean to say that there aren't bits of the climate system that are still fitting the theory, where human forcing is quite slow compared to their dynamics. So we'd have to look for fast bits of the system like monsoon systems, atmospheric dynamics, or sea ice dynamics. So just one more real example. Let's have a look at the Arctic sea ice. We have a satellite record on a roughly daily basis of the Arctic sea ice since about 1979. This is still the record minimum sea ice cover recorded at September 16th, 2012. We've just gone through this year's minimum. It was the 6th lowest on record. And in fact, all of the 6 or 7 lowest sea ice covers have been in the they've been since 2007, yeah. So they've all basically been in the last 7 years. The yellow line is the typical minimum sea ice extent during the satellite record. And this is what it did at the record minimum, about half the ice cover. So you probably heard all about this unless you're living in a vacuum, that the Arctic sea ice is retreating quickly, non-linearly quickly. The satellite record, we've analysed it quite a lot. It's not ideal, it's still a little bit short at 30 odd years. But what we also have are some ship-based records from the good old days when we used to go whaling or whatever up to the Arctic, and we'd go as far as the sea ice edge, and then the ship log would record where the sea ice edge was. We're able to reconstruct the last century or so of minimum summer Arctic sea ice cover, which is this wiggly line here. Take the trend out of that downward falling line and ask whether the fluctuations around the trend have any interesting statistical properties. Well, one thing that's very clear is that variance goes up very robustly in this data set, which is one of the expected warning signals. We can talk more about other physical ways we might explain that signal as well. But yeah, there's some tantalizing possibilities that in that case we're looking at a system that is, we think, heading towards an abrupt shift, and we can even make the case that we've seen an abrupt shift in the sea ice around 2007. So here I'm plotting this satellite recovery of the sea ice area, and you're seeing a huge seasonal cycle, right? The lights are out in the winter in the Arctic, so sure enough the sea ice grows to its maximum extent, usually peaks in about March. The lights come back on, it plummets to its minimum extent in September, and follows a nice, almost sinusoidal curve. But if I just plot the annual maximum and the annual minimum, so the top and the bottom of each sine wave, and I shift the axes a bit so I can overlay them, the annual maximum is in red, and yeah, it's going down. The annual minimum is in blue, and yet it's going down at about the same rate until in 2007 it jumps down an extra 1 million kilometres squared of ice cover, and it stays down. So there's been some kind of abrupt transition in the amplitude of the seasonal ice loss in the Arctic, and that's only the data to 2012, but if I had 2013 and 14, the story would be the same. So we think we're seeing what you could arguably describe as abrupt transitions in the climate system already. I don't know if you're worrying about this in your seats at the moment, but you might have noticed that there's a lot of interest about and a lot of scientific research going on into how the sea ice loss in the Arctic appears to be correlated to the seasonal weather extremes we've been seeing, certainly in northwestern Europe. It's an area of very active research, but we have kind of mechanistic reasons for thinking that there's a connection between these abrupt changes in the Arctic and important changes in seasonal weather extremes. Time's not going too badly, so I got onto the last bit of my talk, which is a bit more fun and broad-ranging, and it's about what might we do about this possibility of abrupt shifts in the climate system. Hopefully I'll provide some food for thought. First of all, obviously I'm barking up a particular tree where I think there might be merit in trying to design some sort of early warning system for the potential of future threshold changes in the climate. Because even if you couldn't then act to avoid those changes, at least you could pre-adapt to what you thought was coming. And that could be very valuable in a monetary and a broader sense of the word. There is a lot of knowledge out there about what makes a good early warning system for a natural hazard, be it an earthquake, or be it some hurricane about to make landfall in Florida, or some other typically much shorter timescale event. I'm talking about, well, I told you, the events might be within abrupt changes within a few years, but they're certainly on a very longer timescale than the prediction of when's that hurricane going to make landfall in the next 24 hours. So whether we can simply map over our knowledge of early warning systems for hurricanes or earthquakes into this realm is not clear, but I think there are some general lessons that come out of a lot of social science research on existing early warning systems, and they tell us that a good early warning system is going to need to have some good risk knowledge behind it, partly in the design of where you prioritise putting your early warning effort. Then you need the kind of scientific technical bit I've just been talking about, the capability to provide some useful warning, and then you need to be able to communicate that effectively to people in a loose sense, and then whoever those people are, they need to have some capability to do something useful about the warning that reduces the risk for them, be that reducing the impact of the event if they can't avoid it, or be it policymakers who then frantically try to intervene in the climate and stop these things happening. So I just want to say a bit about what do we or don't we know about these other elements, and what can we say about that. And what I want to do here is move towards the slightly fluffier or more radical idea that there are also presumably threshold changes that are possible in us as individual humans and in societies, and that they have some bearing on this question of what we do about the possibility of threshold changes in the climate system. But let's first of all just stick with the thresholds of the climate system. The last bit of the talk has been about, can we get better information on the likelihood of these eventualities? If we were doing a proper risk assessment, even in the crudest sense, we'd like to sort of rank what are the impacts of different climate events here, and what's the product of the likelihood and the impact, which is a sort of crude measure of risk. So we draw up some kind of risk matrix and ask ourselves, what's up there in the top corner? That's where I'm going to put my early warning effort. The problem is, there's very little research on what are the impacts of these events transpiring. So if anyone in the room is tempted to join me in doing some of that research, I'd be interested to hear, because I'm just trying to start some of that at the moment. So this is just my subjective judgment about how bad these events are on a relative scale. And it's no more than that, one hopefully reasonably informed expert's judgment. Tim?
Can I just ask, so collapse of Atlantic thermohaline circulation, is that relative to a particular standpoint? So is that because you are a UK scientist in Exeter and it would be really bad for us? Or is it bad for the planet?
This subjective judgment, this is an attempt to give a relative impact between... So let me first say that all of these are high impact events compared to lots of other smaller impacts of climate change that are not to be ignored, put it down here somewhere. That happens to be my reference point on my figure, because that's the one thing for which we've done studies, and my colleagues have done studies. They run a climate model, they collapse the circulation. They don't just look at the impacts on Europe, they look at the global impacts of the changes in temperature, precipitation, monsoon systems, blah, 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 because that's pretty global. It's basically the story I started with of the past abrupt climate changes. Break that thing, and it doesn't just hurt the North Atlantic region, it shifts monsoons in key parts of the world. So that's pretty bad news, and it's my subjective judgment that nevertheless, if we collapsed the monsoon in West Africa, for example, that would be even bigger impact, partly because it unfolds faster, a lot faster. So just my subjective judgment.
So
that from
I don't understand well enough, if we move a monsoon, that's very bad, but is that, so it's your pre-adaptability point, is that moving lots of people from country A to country B, because that's where the rain now is, whereas I would imagine that Greenland or West Atlantic ice sheet melting is London and New York disappearing. because sea levels rise.
Yeah, so exposed assets might be, monetarily speaking, greater ultimately for some of these things. But in that case, it's maybe my judgment's poor here, but in that case, very interesting because the people who live in the Sahel are often migrating in the face of quite volatile interannual variability in the weather. Remember the drought that I grew up with through the 1980s, Live Aid, etc. But yeah, certainly if that happens, people who are already sometimes are quite mobile by our standards anyway are definitely going to be unable to stay in large swathes of West Africa. So yeah, I should reiterate, this is my subjective judgment here on this impact axis could be very flawed. It's really an invitation to people to think about this because it's important from this perspective to get some kind of handle on how what's worse than what, because you have finite resource presumably if you're ever thinking about doing something about these things, be it design an early warning system. So you're going to have to do some prioritization exercise. You need some information to base that prioritization on. You need a risk assessment, and we should ignore this in the sense where we should say this is inadequate, but we ought to be able to do this. Okay, so yeah, things get a bit woollier now, but I'm thinking, okay, this is just a looser, broader point about climate change. Clearly, socially, collectively, we're not all on the same page about this. We might be in the UK, we certainly aren't in the US and several other places. But there's good theory. People who study the theory of how we hold worldviews, like I believe climate change is caused by human activities, or I don't believe climate change is caused by human activities. People who hold conflicting worldviews, those worldviews are coherent within their minds. And there's a philosopher, Paul Thagard, and colleagues who work on literal computer models of people holding the coherence of their worldviews and what it takes for them to shift worldviews. And they've done a specific case study on climate change, by the way, showing how we're not purely rational actors. If we have a strong belief in avoiding oil limitations and avoid government intervention, sort of neoliberalist belief system there, perhaps that can stabilise a view that humans do not cause global warming. I'm not trying to make any particular point about that, just to say thinking in terms of tipping points is also instructive when we think about what would be required socially to actually do something about the danger that changes in the climate system pose. We have to think about ourselves as perhaps having to tip our own thinking. We certainly have to think about, can we tip our collective action as a society, right? And here I'm very interested in work in game theory economics, whatever you think of that. Some of you probably got a pretty dim view of that, like you have of the general equilibrium models. But so Scott Barrett, Astrid Dannenberg have been doing some work on this, and this pertains to the early warning question, because what they did is they said, okay, Tim, you think you get this early warning at a tipping point, but you've got some uncertainty range on your warning. It's not perfect. How about I treat that uncertainty range as my x-axis here, and I ask myself, I give these some students in this case, it's usually students in game theory, economics, playing the games, right? I give them some chips, they play a game where there's a danger of a catastrophic outcome, a climate tipping point in which they're going to lose 100% of their chips or 90% of the chips or whatever. Can they coordinate to put enough money in the pot to reach some nominal target to mitigate and avoid that threshold? And the answer is basically, if the uncertainty about where the threshold is too large, they fail to coordinate, get enough money in the collective pot. We get a classic prisoner's dilemma, tragedy of the commons. Hopefully you're familiar with that kind of language. If you can narrow the uncertainty enough, so if your early warning system was good enough that you could really nail a bit better how close you were, where the tipping point was, then the social system here tips into a different dynamic. It tips into a coordination game, as the game theorists call it, where the group try to coordinate to make sure they do put enough resource in to avoid that eventuality. So I think that's...
I can't this not start asking a question here, but these public goods games, everybody will be familiar with them, and there's fascinating results. One of them is that it's easier to entrain people in playing fair if you can punish. But then there's a fascinating study that shows if you do this in northern countries, that really helps. If you do it in the Middle East, identifying a punisher, then people go bananas and the whole thing collapses. If anyone gets punished, then they punish the punisher and the whole thing collapses. Even more interesting, I think, for a long time I felt these public goods games relating to climate change need someone to look at them in which instead of each round everybody starts off in the same position. You ought to be more like the real one. Some people start with more and have to put in more. And out of that came a really interesting finding that we never thought of. The group of people you sort of hire in Oxford contained quite a few women. And very statistically significant. Women are much more likely to cooperate than men in these goods games.
So excellent points, Bob.
How many women are actually involved in all this stuff?
Well, that's one was a co-author, and in the study is a great question because it's well known. I mean, when we do this stuff in Exeter, we do a whole lot of recording of risk preferences, etc., of our participants. But excellent points, basically. I mean, here I'm out of my own professional expertise zone, but just throwing out some provocations, and I think your points are really well taken. There's nice work, Alessandro Tavoni and Alessi, I think, here in London. Various groups are trying to take this forward. But of course, the reason why any of us would be thinking like this is because we are all sat staring at what looks like a profound stalemate of the last 20-odd years in international negotiation to do anything about the climate problem. So we've, as academics, of course, rather than just bang our heads against the wall, we want to try and understand what's the nature of that stalemate and could it be broken. Here's another provocation then, where if we begin to think about, okay, we think these tipping points are coming, we know that we could take our foot off the gas of fossil fuel burning in principle if we could construct some way of that not buggering up the economy, etc., by shifting the burden of taxation. So maybe we might put a carbon tax in, and as long as we were clever and we explained to people that we were just moving taxation around, maybe there wouldn't be a mass rebellion, but no one had the bravery to actually try that, except possibly Australia, and then they backed off. Anyway, let's not get into that. And what I'm doing here is after like 20 years of resisting, resisting getting into economics, I got interested in what are the economists up to in their attempts to model this problem. Doyne touched on this earlier, but you have a lot of very crude, actually purely deterministic cost-benefit analyses, integrated assessment models they are, sort of toy models of the climate and the economy coupled together. And the purely deterministic dimension of them was what most troubled me when I was thinking about tipping points and thinking about the climate dynamics and knowing that there'll always be a stochastic component, a white noise in the system. So I just, last couple of years, started collaborating with quantitative economics people who I'm afraid are still in a stochastic dynamic general equilibrium framework, but at least they're using supercomputers to do the problem now, because we have a stochastic dynamic climate coupled to a stochastic dynamic economy, and we've got a 200 or 300 year planning horizon, so there's a lot of very smart computational work that has to be done to run that model 10,000 times and get a distribution of results for the optimal policy, which is clearly not optimal, as you said earlier. But you know the game here. All I wanted to say was, maybe it's an obvious result, but if you put the possibility of a tipping point in these models, and you might say, but it has a stochastic quality to it, so it's a hazard, it has a hazard rate, that hazard rate might go up as a function of temperature, but still each year I've got to roll the dice to see if the event happens or not. The dice is getting weighted as the temperature goes up, but still there's that stochastic component. You put in a kind of textbook view of known risk aversion of people, pick your preferences. I'm starting to learn about the lingo of this, Epstein-Zinn preferences. I know there's all these different ways, different sort of choices about the risk preferences in the model. But if you put in a perfectly standard view on risk aversion, you put stochastic tipping point into the future, you can have this tipping event unfold quite slowly. So we can now capture a transition time, like ice sheets take 500 years to melt, or it might take 50 years to kill off the Amazon forest. That's what's on an axis here. We frankly don't know how much these events hit world GDP, so we might vary it between 2% or really bad news, 20% like the Great Depression. And we plot out what's the extra carbon tax, what extra should you be willing to pay now to try and at least delay the tipping event. So that's the carbon tax there, and that's the consequent delay in years, and they're actually almost one-to-one. Each dollar buys you a year in this particular model. But I guess the point, what was interesting that came out was not that this should bump up how much you're willing to pay now, because of course it would, when you put in an extra future hazard. But when you look at how this extra carbon tax to delay tipping evolves in the model, it turns out to have its own discount rate that's a lot lower than the typically assumed 3% social discount rate in these models. It sort of has some discounting. It's usually around 0.8%, something like that. But what that is apparently to economists, that's like how an insurance policy behaves in the theory. And that's kind of intuitive to me as a climate scientist, that what comes out of this fairly, you can call it crude or fancy modelling, is a simple result that we should respond to the prospect of these stochastic future events with large impacts by buying some insurance against them. All right, nearly there. So then, let's say, okay, let's imagine we do start to act, or we want to act, or somebody does start to seriously put a carbon tax in place. Then you still have to ask some questions about what's it going to take to transform the energy system from backstop fossil fuel energy to something else. And I threw this in because I was interested that amongst the many models that exist of the energy system and possible transitions in it, there is one or two where you also see kind of non-linear tipping dynamics in the energy system. So here your control as a policymaker or whatever is to dial up the carbon price. But the black line here is a model where, as you're ramping the carbon price up into the future, you can actually bring it down again, but still in that particular model, you can't stop the transition from fossil fuels in grey to what in this model is a renewable energy backstop technology. And it got that result through having some technology transfer feedback dynamics in the model. But because I'm like naturally inclined towards thinking in dynamical systems, I think it's appropriate also to think about, well, the energy system is in some sense a ball in a valley with quite a range of subsidies and other things that are stabilising the current fossil fuel backstop technology. Presumably you can imagine another valley with a ball in it which is renewables or nuclear as your backstop energy with its own subsidy regime or policy to reinforce it. And of course the question is how to get from one to the other, and that's what this model was about, that it might be like a tipping process. So we might mitigate climate change, although we haven't yet. We might rather mitigate fossil fuel emissions. We're all familiar with that idea. Of course, the prospect of really bad things kicking off in the climate has also provoked some people to suggest more radical interventions. So they talk about, there's this idea of geoengineering the climate. You've probably heard about it in the news. Should we, in one case, inject sulfate aerosols into the stratosphere, the bit of the atmosphere with the ozone layer in it, and thus cool the climate? And this is often framed, actually, in the Royal Society's report, I'm sad to say, as well as in other contexts, as the rationale being, we have this as an emergency response if we think the climate system has already passed a tipping point or is approaching one, if indeed the early warnings worked. So that's a popular framing, that we kind of develop geoengineering in the back pocket in case emergency, whatever that means, is declared or is perceived, and then we throw it into the climate system, a strong cooling intervention. What I want to say about that is just a few things. One is that there's lots of unintended or understandable consequences in this case for ecosystems, if we were to inject sulfate aerosols in the stratosphere. And we might indeed make a case from past volcanic eruptions that have done the same thing, that sulfate aerosol injection could disrupt monsoon systems, and certainly did, in the case of volcanoes, did dry certain parts of the world and historically caused problems with food production. The other point to make is I'm not sure emergency geoengineering would work in a dynamical system sense. So remember my example that the Amazon rainforest was lagging the climate forcing, because as humans we're moving the whole system quickly along the x-axis. There's no really good way to plot this, but we started the talk with a plot of one of these kind of tipping points, and this is literally mathematically the equilibrium solutions of a system. And now I'm talking about a case where we're not at equilibrium, the system's lagging the forcing. The only way I can cartoon that is to sort of drag the system. It sort of stays in this state even though it should have lost its stability, and it's dragged over here, and then it starts to change abruptly. So that's your emergency, where you intervene with geoengineering. The problem with that is you're in the basin of attraction for the other state. Now the system really, really wants to go into the other state, whether it's whatever part of the climate system we're talking about here. So you intervene frantically to cool things down on the x-axis, your remediation effort, but you're fighting the system's own dynamics that want to go off into the other valley here. And God knows what trajectory you go on through the phase space. Maybe you eventually recover the system, but you might have had to over-geoengineer and end up cooler than you wanted to be or you started with. It becomes a dynamical system problem, or I like to think of it as the Looney Tunes example, where roadrunners chased Wile E. Coyote over the cliff edge, but he manages to hover in the air for several seconds as he's lagging the forcing before gravity takes hold and wants to take him into the alternative state at the bottom of the cliff on the ground. And geoengineering is kind of, he starts to fall and then you think, shit, I better intervene. Can you get him back on the top of the cliff? Anyway, I've said enough. So early warnings exist. The methods exist for this class of tipping points, bifurcations. They've been tested successfully on some past examples from real data and from models. Sometimes they fail, but we understand why they fail if we think carefully, because they're violating the underlying theory, like we're forcing the system too quickly compared to its own dynamics. That leaves us a subset of climate tipping points where you could still potentially get an early warning. And some of those will be the fast kind of dynamic systems, including monsoons, which you could argue, if they were tipped, would be the worst case scenarios of all. So still some merit, I think, in thinking about developing early warning systems for them, if only as a trigger, as an aid for adaptation. I don't think emergency geoengineering is a sensible or necessarily workable response to those kind of abrupt changes. Conventional economics, whatever we think of it in this room, suggests that the optimal thing to do in the face of all of this is certainly to mitigate emissions as an insurance policy against these things, at least to delay them. Thanks.
Thanks, Tim. That was terrific. Any of us who weren't worried before this talk should be so now. And how long have you been such a strong proponent for geoengineering?
Opponent.
Proponent. I'm kidding you. Sorry.
Well, the funny thing is, many of my colleagues think I, in many ways, encourage people to look at the subject again, because around the time of what is actually a very good 2009 Royal Society report, that's just around that time I published a paper trying to quantify the cooling potential of different methods, and that got a lot of attention, a lot of major attention. So it may appear that I've done an about face, but really, I mean, I think this often happens. We, as scientists, we were kind of desperate. We're staring at the international negotiation stalemate. We're thinking, nothing's going to happen. Is there any other dial available in the Earth system, in the climate system, to do something about unfolding dangerous climate change? And so you feel compelled to at least have a look. Then you think about it further. You acknowledge your own ignorance of the system, frankly. I mean, you think you understand it, but you know the limitations of your models. And then you back off, actually, because you realise it doesn't make sense to intervene in a radical way in a system you don't fully understand.
I have two comments on that. The Climate Change Committee is firmly against the idea.
Which is great.
The Climate Change Committee in the United Kingdom is firmly against that idea.
Right.
And secondly, my impression, which may be incorrect, is that the Royal Society did it essentially, because I read the report, it's simply saying what you said.
Yeah.
And I think the Royal Society did it just to stop being pestered by a bunch of nitwits.
Yeah. And it's a very good report, and there's about to be a revision of it. And I think what happened is a committee job, like all these reports are. And what the reality is, there are some people on the report who think that the emergency framing is valid, others who deeply disagree with that. Yeah. Thank you for
Other questions for Tim, Roger?
Yeah, I thought that was terrific. Thank you very much. What I wanted to just test was, from an economic point of view, the Martin Wolford, who speaks for some of us, wrote in the FT something along the lines of, humanity has decided to yawn and let the real and present dangers of climate change mount. You know, and just juxtaposed with your last statement there about conventional economics, the belief system that exists in the world I inhabit, which is asset management, is very clearly, it hasn't adapted to the reality as seen by climate scientists. I would argue that very strongly. So one of the things I would argue for is you early on gave a bit of narrative about experts being quizzed and sort of systematically putting certain probabilities around those tipping point events. And that is the sort of codification of soft stuff into slightly harder real data, as it were. Because I think at the moment I'm very confused with really the pace of change with respect to the climate. You know, if you take The Economist of about 6 months ago, basically saying climate change has stalled, you know, that's one interpretation that you see out there. And indeed, at one point in your talk, you kind of gave a sort of narrative where 2 degrees, 3 degrees was within the 2030, 2040 area, which, as I would see it, is not consistent with the pace that we have at the moment. Now,
correct on that point, in that we've seen this slowing of warming in the last 10, 15 years. At some point, we're going to see a very rapid interval of warming if we think about that slowing down as natural variability overlying an upward trend. So it's when what would have naturally been a cooling is sort of slowing the warming. And eventually we'll get what would have naturally been a warming adding to our warming, and we'll ping upwards. But we can't say, or rather models are currently disagreeing when we'll get another rapid warming like we saw in the 90s and 80s.
And I think that's exactly, in a sense, my point, that the belief systems that people have are going to be more rudimentary, and they're kind of, there's a lot of misunderstanding, misinformation that it's endemic in the finance world. Now, obviously I deal a bit with, let's say, some of the corporations that have big carbon footprints of one sort or another. And the basic way that they look at the problem is that they will adapt as appropriate, and the world needs the energy. Now, in some respects, it therefore becomes, I think, critical that the debate is moved on, you know, quite substantially, and therefore I think the interesting thing about it is the people in this room have a certain amount of influence on that ownership of the carbon footprint itself. So whether or not we're talking about public policy, or whether or not we're talking about, in a sense, the kind of invisible hand of capitalism and the guided hand of capitalism to make some of those adaptive moves. And I'm coming back to, I'm very interested by the clarity with which climate science can give more clarity to the trajectory of change, because at the moment I don't find it very easy to read that.
Great points, I think. And I vary on a daily basis my gut instinct about what we are going to do about this, if anything. And part of the reason I put a lot of effort into this thinking about early warning was because of the lack of action on mitigation. I perceived as the default position that we'll just keep burning, as it were, but we are an adaptable species, there's no doubt about that. And that might be that sort of null model assumption, in fact, that we're just going to try and ride it out. And therefore, my kind of moral compass says, well, if I can provide some useful scientific warning about the bad shit that's coming to help us adapt, then I'm in a kind of internally, morally better place. Of course, I'm also giving you a message that, I still think the wise thing to do would be to reduce the cause of the problem, but I'm realistic that there's no evidence that we are doing that as yet. And you're quite right that you could argue that part of that is a failure in risk communication by the climate science community. I think that would be a fair accusation. I think we could have framed this much more clearly in a risk thinking way that you and obviously the economics community are very familiar with. And one can be cynical, and Bob will probably have some good views on this, but one could argue that the construction of the Intergovernmental Panel on Climate Change and this rolling 7-year report and this intergovernmental thingy was, if you wanted to design something that would lead to inaction, you couldn't have done a much better job than that. I shouldn't be heard to say that in public, because it's sort of insulting all the years of effort my colleagues and myself have put into it. But I think, I hope that just with a slightly different perspective, thinking about these high impact events, it helps us get into more of a risk management thinking space about this, that should it all have to be predicated on, what the temperature's been doing in the last 10 years, which isn't meaningful anyway from a climate point of view. It shouldn't be predicated on that. It should be more like, I was going to say, you guys and you girls. I mean, some people are willing to throw huge amounts of money at saving the euro or whatever it is. In the same way that they're not willing to spend the same orders of magnitude on this problem that I think is at least as well, in a complex systems sense, I'd argue is better understood than the economy, even though the understanding's flawed, at least as well understood, let's say. So that has to be something wrong in the framing and communication.
Tim, thank you. Fabulous talk. Sorry for interrupting you partway through. I think you said business as usual is 4 degrees C warming.
And then some, depending on how far you want to talk into the future.
Okay, so what date's on the 4 degrees?
Later this century. And then because there's inertia in the climate system, you're actually committed to carrying on up. And how far you're carrying on up, whether it's 8 or 6 or 10, will depend at that point on how much of that known fossil fuel is it really going to be economically rational to extract or not. And arguments still rage over that, but we know that, unfortunately, there's enough fossil fuel in the ground to carry on up to 8 or 10 degrees of warming. We ain't going to do that because by then, large parts of the world, the temperature, the heat extremes, the heat wave extremes are intolerable for our existence. So,
okay. So my next question was going back to kind of like your game bit, where you need to reduce the uncertainty. What's the range from climate scientists such as yourself? Are you 95% unanimous that it's 4 degrees plus, or?
Well, so the devil in the detail of your question here is, in order to make a statement about future temperature at some time horizon like the 2090s, we're going to have to predicate that statement on some assumptions about the path we take in the meantime of fossil fuel burning. Because although the rate at which we're burning the fossil fuels doesn't affect the temperature trajectory in the models for the next couple of decades, by the time you get out to 2080, 2090, it really matters whether you've carried on a business as usual, sort of almost exponentially rising combustion of fossil fuels, or whether you've gone on a mitigation trajectory. That becomes the difference between a 2 or slightly less than 2 degrees warmer world or a 4 or more than 4 degrees warmer world. So if I predicate my answer on, so I have to give my answer in terms of some underlying assumption When we talk about business as usual, what we would do, in my case, I would take the last 25 years mean growth rate of CO2 emissions is 1.9%, and if I extrapolate that forward, I can tell you what temperature that will give with an uncertainty range on it, but it's ballpark 4 degrees. And the science behind those ballpark numbers is 19th century physics of the greenhouse effect and calculations that Svante Arrhenius made calculations in 1896. Pen and paper took a couple of years. He was depressed. I think his wife had left him or something. But he calculated the climate sensitivity in the 1890s. He got quite a high value, but one that's still in the range that we talk about now. Which is to say, how much warming do you get if you double the level of concentration of carbon dioxide in the atmosphere from the pre-industrial level. So those kind of numbers are robust once you understand once one's clear about the assumptions behind them.
So final question, for us lay people, how urgent is it for us to change the incentive structure now, to change behaviour now?
Well, maybe I give a sideways answer that I think I'd rather my kids grew up in that world where we had changed the incentive structure and we did make the transition to a different backstop energy system sooner rather than later, and we did switch to a more of a material cycling economy that's powered by sustainable energy, because I, for various reasons, perceive that will be, in other social dimensions, could be a happier and healthier world. So I could make the case, as I've probably just done for an hour, that there's an urgency, that you could perceive an urgency to do it from a kind of negative reasons point of view. But the negative reasons have been with us for the last 30 or 40 years, however well or poorly they've been articulated. So I honestly think the way forward is to find a narrative about the future here where we say, well, what kind of world do we want to be living in 2050? We know, Bob knows, we know what the population is going to do roughly, we know the challenges that poses for land use, we know the parameters we've got to work with here, but we can ask ourselves, as a mature society, we can ask ourselves a question, okay, what kind of climate, what kind of world in a much broader sense do we want to work towards, and use that kind of positive vision in a way as a reason to compel action, because all the bad reasons have not compelled action. So that's a sideways answer, but it's the one I've come to in my own thought.
Can I just add one other thing about this? It occurs to me not everybody is familiar with what Britain is doing about this.
Yeah,
it relates to the 2 degree, 4 degree.
Exactly.
We have primary legislation that commits us to a trajectory which was proposed by a committee and is accepted by government, and it is one which commits us, the estimate is if we do achieve such and such a target, then we will not, if everybody in the other countries did the same, we would not have exceeded the 2 degree, we would have come to a point where we settled and we hadn't exceeded 2 degrees. We are actually, rather surprisingly, still on that trajectory in this country because a lot of people don't like it, and we've got a lot of climate deniers with quite lavish funding from people in the States. But the fact that we are on trajectory for this so-called legally binding target, if you ask what happens, in what sense is it legally binding, and nobody really knows, but we're on it partly by virtue of the recession. Whereas it's the one thing that the committee has failed in. The committee wanted that to be, did not want that to be counted. It wanted to bank it, and it couldn't. But nonetheless, that's the sort of thing we need to be doing more generally.
Absolutely.
Please continue to set a good example for certain other countries who aren't doing quite as well. Not pointing at anybody in particular. Any other questions? Okay, please join me in thanking Tim.